Here I have a hoop. It's actually a bike tire, but you get the idea. And we've taped some very heavy ball bearings in the side here. So the question now is, if I was to roll this hoop with a point mass, substantially heavier than the mass of the rest of the hoop, when it gets to here, will it just accelerate down, or will this coming down under gravity lift up the rest of the hoop and give us a hopping action? Well, the first person to ask this question, at least in writing, was Littlewood, a British mathematician at Cambridge, who in 1953 wrote a book called A Mathematician's Miscellany. And the introduction basically says that Littlewood could not be bothered coming up with some kind of theme or general concept to hold all the bits in the book together. I aspire for that kind of reckless abandon when it comes to writing popular maths books. However, a few pages in, he presents this exact concept. Here we go. A weight is attached to a point of a rough, weightless hoop, which then rolls in a vertical plane, starting near the position of unstable equilibrium, which is to say the weight is right at the top. What happens, and is it intuitive? Well, I thought I'd give it a go. And according to Littlewood, this hoop will hop if released to rotate, and they don't do a lot of mathematics. There's like one extra paragraph, a little bit here where they go through it. But several decades later, Tadashi Tokieda, who you may know from their fantastic Numberphile videos, wrote a quick 2-page bit of mathematics. This was in 1997, showing that yes, the hoop should hop when that mass is on its way down. But then these people disagreed. So before we get into what several papers, which, I mean, I'm not saying that mass is the best indicator for mathematical value, but a lot bigger than what was happening here. Before we go into those, I thought we'd just roll some hoops. We'd see if they hop. So we got this one, which has got the weights inside a bike tire. We also got this one here. So that's some metal weights, and we've got sandpaper on the outside. It's got to be a rough hoop. And as you can see, I mean, if you roll it slowly like this, weird kind of lurching action, we can do a lot better. We've also got this one. It's got teeth, so it digs into whatever surface it's on to stop it from slipping. And there's a very heavy mass built in there. So we're going to take all of these out into the hall, see what happens.
Yes, the tire has a bit of a bounce to it, but don't worry, the wooden one does hop. See? That's a hop.
Before we get down to hoopness, I want to mention that this video is part of the Stand Up Maths Mental Health Season, sponsored by BetterHelp.com. That's H-E-L-P. They have over 10,000 licensed therapists that you can contact to help you with your mental health. But the point of the Stand Up Maths Mental Health Season is not that you necessarily have to go to BetterHelp. There's loads of other places where you can get support. In this video, I'm going to be highlighting the fact that if you are a university student, or maybe you work or study somehow at a university, there may be free mental health support available. That was one of the times I got therapy myself. When I was an undergraduate at the University of Western Australia, they provided therapy sessions for undergraduates, and I took advantage of that, and it was super helpful. So if you're at a university, do see what support they provide. If you're not at a university, you may have other access to mental health support. And of course, betterhelp.com, H-E-L-P. Help. If you go on there, you can answer a few questions about what you're hoping to get out of therapy, and they will match you up with a licensed therapist anywhere in the world, and you can start communicating with them online through either video chat or messages. Thank you very much to betterhelp.com/standupmaths for sponsoring this mental health season. Finally, BetterHelp is not a crisis mental health support service. I will link to some of those below if you want to check those out. And that's it. Now it's time to get back to Better Hoop. We managed to get these hoops to hop out in the hallway. The question now is, does that count? I'm not gonna lie, we really had to give them some serious angular momentum. Yeet them, as the kids would have said about 5 to 10 years ago. Anyway, the point is we had to move them pretty fast to get them to actually hop. And my friend Lisa Mather made these for me, and we were actually doing a geometric installation at a festival last summer. She brought along some of the prototypes. We realized if we moved them slowly, they absolutely did not hop, but if we gave them a real angular momentering, as the kids will say from now on, they did hop. And we were pretty pleased with that until sometime later. Katie Steckles, who was there, who you may remember from previous videos of mine, sent me a hopping hummus, because an unbalanced container of hummus would indeed hop, which leads to my first conjecture that any unbalanced wheel, if yeeted fast enough, will hop. The wording is not final, but the point is, I think if any kind of disc has an imbalance in the mass, there's a speed such that it will hop, which is not the original question that Littlewood was trying to raise. To recap Littlewood's setup, we've got a point weight here on the top of a rough, which is taken to mean infinite friction. Not going to slip, which we've done by using the little kind of saw teeth, and we've got this non-slip mat on the table today, so it means this is never going to slip. Weightless, which means all the mass is here. Technically, no mass down here, and it starts near the position of unstable equilibrium, and the position of unstable equilibrium is that one there. Because technically I could balance it right there. Ooh, it's an equilibrium. But it's so unstable, like if it's even slightly off, away it goes. And so the idea is you start with it here, you gently release it, and then you allow it to roll. So you know what? We've got it all set up here. Let's do some slow motion of that happening. See if we can catch the hop in action, starting from a standstill. Oh, that didn't work. And according to Littlewood, it should have. Littlewood says here, the hoop lifts off the ground when the radius vector to the weight becomes horizontal, which is that position there. And you will have seen in the slow-mo that that puzzle seam was directly down when it should have been hopping. And they say the motion is equivalent to the weight sliding smoothly under gravity on the cycloid it describes. Pretty intuitive. And it will sooner or later leave that. Huh. Well, that doesn't clear that up at all. Thank goodness Tadashi was on the case. There are two shapes we need to follow Tadashi's argument. One of them is the cycloid. That's the shape you get if you follow a point on a rotating wheel. So if you imagine, if I start that there, you got, let's take the middle one of these three. As I rotate it down, it becomes a line coming down like this. It hits the ground and stops, and then goes straight back up again as such, right? And this shape here, this is a cycloid, and you could carry that on, and so any point on a wheel will trace out this kind of bouncing pattern. Not a parabola. But the parabola is our second shape. So if I had an object, I'm going to use this dice. This is going to represent, again, just the middle one of these masses. This is a point mass. If there was no wheel at all, and this mass was moving, it would follow a parabola. And that's what the shape would do if there was no wheel. However, the wheel has no mass. So we've kind of got two conflicting shapes here. The point is technically on a wheel, so it should follow a cycloid, but yet the wheel's got no mass. So it should be following a parabola. We need to plot and compare both those shapes. It's GeoGebra time. So we've got a massless hoop in blue and a point mass at P. And you can see there's some angle theta. We're measuring that from the vertical direction. And I can move theta around manually to make the hoop roll, or I can just start animating it. And there it is, rolling as if gravity, did it hop? Who knows? We'll find out in a second. So I'm going to reverse that back up again. And so if you think about the path that P is tracing out from before, that's our cycloid. And actually I can turn that on. There it is. And now, as I animate the hoop going backwards and forwards, you can see P always stays on that line. Now actually, we're not going to see it hop in this animation because this is not a simulation, it's a diagram. So it's not like we're numerically simulating what will happen. We're actually just animating the circle moving backwards and forwards. So we're not going to get any additional insight into the actual mechanics from what the circle does. The insight is what happens if we turn on the parabola, because you can imagine at any point in the rotation of this hoop, if the hoop was to suddenly vanish, this would continue moving along a parabola. So actually at all points in time, there exists a parabola that this is on that shows the motion, if it was a projectile, to be at the same place and the same velocity as if it's when it's rolling on the hoop. So the parabola is what would happen if the hoop suddenly vanished. And I can turn that on here. There it is. That green line is the parabola. So that's like the phantom parabola. If there suddenly was no hoop, but the particle's still there, it would carry on along that. So if I move it backwards and forwards, you can see the parabola changes as the hoop rolls. It's very cool. And the question now is, does that parabola always stay inside the cycloid? And if I'm going to animate it through. So you watch the parabola and, oh, did it? Or did it flip outside? If I go a little bit further forward, look at that, it's outside. And so that means at that exact point here, the projectile path is outside the cycloid motion on a wheel path. Because if it's inside, basically means it's just pushing into the wheel. That's not going to happen. But if it's on the outside, well, this is what Tadashi argues, the moment that parabola is outside the cycloid, it means we're going to switch from rolling wheel motion to projectile motion. And that means the hoop is going to hop. Now, we didn't see it because obviously this is not zero mass. This is made of wood and there's the friction. We've tried to go for no friction, but the point is our physical model wasn't a perfect enough recreation of the pure mathematics. But what's mentioned first of all by Littlewood and then done in detail by Tadashi is that in theory, the hoop should hop. Nope, at least according to, at a minimum, this paper, hopping hoops don't hop. So this was not the final word in 1997. We have a lot more mathematical publications about the hopping hoop. All of these are from 2000 onwards. I'm going to put them aside for now and look at these two from 1999, which pretty much have the same argument. So I'm going to pick the one that actually says hopping hoops don't hop, but we have also got the Hopping Hoop Revisited, which came out like a month. This one's like July. This one's, no, June, July in 99. This one's from the August-September publication. So the general argument here is that the hoop has to slip. So they're saying that's all well and good to have your argument here where the mass comes down and then the parabola goes outside the cycloid and hop. But they're like, well, hang on. How is it going to hop like without slipping? So to hop, assuming infinite friction, it would have to go like straight up somehow, but there's always going to be some element of slipping. And I'm very much paraphrasing some long involved mathematical arguments, but they say no. If we retain Newton's laws, which we probably should, that's kind of the whole point here, and an impenetrable floor, which means the hoop can't go below the surface it's rolling on, then the no slip condition must be violated when n equals 0. So that's like when it would hop, implying that the hoop skids. So they're saying when you get to the point here where it should hop, it can't hop. That doesn't work like in Newtonian physics. The only thing that can happen is it has to skid. There's no way you're going to get a non-skidding hop. Or so they say. I will say there's one final conclusion in this paper that I absolutely love. At the very end, they've got a final theorem. The behavior of hopping hoops is not intuitive, which is what Littlewood originally raised. And they state that as a theorem, and their proof is by inspection. If there's anything we can agree on so far, it's that. Final 3 bits of mathematical research that came out between the year 2000 and 2009, and this is when people started to take the physics a bit more seriously, and they're like, look, instead of assuming that the hoop is massless, that's ridiculous, let's look at the ratio of masses. So the hoop has got some mass, and there's some ratio, which they used a gamma to represent, that's here as the point mass. So that's just an unbalanced hoop. And instead of having infinite friction, let's just have a coefficient of friction. What's wrong with mu? Bring mu back in again. So now they were able to model an unbalanced hoop rolling on a surface with some friction. And it turns out, first of all, if we put hopping aside for a moment, which I know will make some people hopping mad, a little joke there for all the joke fans. For the mass fans, however, there are actually 3 things a hoop can do when it's rolling. You've got the actual rolling action, that's kind of the default behavior. You've also got slipping. So if there's not enough friction, you might get a slipping effect where it rotates this way. And interestingly, the friction force is acting in that direction if it's slipping this way. You've also got skidding. Now that's different to slipping. Skidding is like the comedy coming to a halt. That's the effect, in which case now the friction goes that way. So slipping and skidding are distinguished by the different directions that the friction is acting. And in a more realistic universe where we do have some non-infinite friction, it turns out both those things can happen when you release a hoop with different amounts of initial angular momentum. But we've got a lot of variables now. We're going to need some diagrams. Some phase diagrams. Phase diagrams. So each one of these individual plots is for a specific combination of mass ratio and coefficient of friction. In fact, the top 4 all have the same mass ratio where 3/4 of the entire system mass is in the point mass, and then they gradually ease up on the coefficient of friction. And then on the vertical axis, we have the amount of initial angular velocity. So you pick a point on the vertical axis for how fast you want to start this thing going, and then as you move across horizontally, that's the rotation, theta as it's rotating, and it tells you what happens. If it's hashed, it means that it's rolling normally. If it hits a D region, that means it's skidding. If it hits an S region, that means it's slipping. And so if you look at this, you can pick your starting point for whatever combination of the physical setup you want, and then you move across and you're like, oh, it's rolling, and now it's slipping or skidding or doing whatever, and then eventually something interesting might happen. It might repeat, so if it gets to the far side with no blank spaces, it means nothing interesting happened. If it hits a Z, that's the 0 line, that means it grinds to a halt, and if it hits an H, that means it hops. There you are. Those are the hop regions, and as you may have noticed, they're all at the top, which means high initial angular velocity, which means if you yeet something, it shall hop. Still working on the wording. Now I just need to bring this video gently rolling to a satisfying conclusion, and I will say that this kind of exploration of the actual physics is super interesting. At the very end, they've got a table of all the different combinations of things the hoop can do. Like you can see here, it can roll and then slide and then roll and then skid and then roll again and then slide, then roll, then skid, then roll. It's so interesting, all this going on. And I'm not the first person to like make hoops and see what happens. Tadashi, way back here, did that. They say at the very bottom here, we taped a battery on a hula hoop. I mean, that's pretty much what we've done here, I'll be honest. And rolled it along the 12th floor hallway in Fine Hall. That's at Princeton, and it says it actually hopped. I suspect that's a case of just, you know, the yeet situation. And then over here in one of these papers, they've got a fantastic, there it is at the back, there's a shot. They got a hoop, they put a mass on it, they rolled it, and they showed, once again, if you give it a bit of speed, it will hop. And the very last paper from 2009, this is pretty cool, they got a hoop, actually not dissimilar, where's mine? This kind of a setup, and they put LEDs on it, so they could more closely track what was going on. And they released it on a variety of different slopes because the increase in slope meant that you'd have that extra speeding up which will cause it to hop. And they found that sometimes for very severe slopes, it would hop on the first rotation. And there's like a range of middle slopes where it wouldn't hop the first time the mass, like the point mass came down, but it would hop on the second one. Very cool. And actually this validated a lot of the the physics papers that came out between 2000 and 2009, and it dissed these. From the conclusion here, they say, first of all, our results support the predictions made in reference 5, and their reference 5 is the 2000 paper. So this was theoretical maths. They then did the experiment and showed that it all lines up. Very good. However, they do say the experimental confirmation that the hoop hops at, and then a range of angles, supports equation 11, and contradicts reference 3. That's this one, the hopping hoop revisited. So this physics, they're like, no deal. What a math smackdown. Those are some harsh words. Look at that. Contradicts reference 3. Please. Language. From the conclusion of this paper, they also say that the 99 theory doesn't work, and they say that what Tadashi Tokieda and Littlewood were saying doesn't work either. So from here, therefore, and this is the situation for the massless hoop like originally set up by Littlewood, therefore the hoop will hop as suggested by Littlewood and Tokieda only if there is a discontinuous increase in the angular acceleration, which is a fancy way of saying it doesn't work in terms of like physics as we understand it. They actually introduce a new concept called skimming, which is where the mass has switched from the cycloid to the parabola, but the hoop is now kind of levitating along. It's skimming, not skidding. It's skimming along with it. So it doesn't actually hop. So, I mean, the grand conclusion is, I don't know. They are. We don't know. Someone else wants to make a bigger, better hoop? Let me know. Or some more maths occurs? Let me know. Or I've missed something. Please do let me know. But, I mean, the yeet theory is correct. These papers do prove if you've got an unbalanced wheel and you move it fast enough, it will hop. And to Littlewood's credit, back in 1953, they did originally put the very last line in their setup. In actual practice, the hoop skids first. So even Littlewood, from the very beginning, knew that you probably wouldn't actually see this with a hoop, because in reality, it's gonna skid. So, although we since renamed that slipping. What are you gonna do? Point is, we had a lot of fun building the hoop. So huge thanks to Lisa Mather and Joel, who helped out with 3D printing this and putting these hoops together. Thanks to Ben Sparks, who did the GeoGebra file that I was showing you before. And thank you to everyone who watches these videos. I hugely appreciate it. And in exchange for you obviously liking and subscribing, come on, I got Steve Mould to catch, I'm going to show you 20 seconds of slow motion footage of a hopping hoop being chased by my dog. Please watch it and take that time to subscribe.